So meeting event or anything of that type here. Event center, meet calendar. Yes, there are people who. ISFE 9 a.m.
Logo on the lower right corner.
Okay.
Down corner on the WebEx logo.
Here,
That one green circle. Yeah.
the white. Yeah, this one. Privacy.
Yeah. Or it's on our screen.
Seeing anything. It then ISFE join webinar. I don't join that, is it? Okay, sorry. Let's go to home. But can you screen now?
Yes.
Is that the one or meeting center? Ether.
With the escape key, you exit the screen mode.
So again.
With the escape key, you can exit the share screen mode.
Which sorry, what is the key you said?
Escape. ESC.
Oh, ESC, yeah, and then.
Oh, it didn't go. Let me contact the guys here in the
Okay.
team.
Okay.
Hello.
Sorry?
Yeah, I can hear you. Yes.
Okay, can you see me now?
I can only see your screen.
No.
I can only see.
Okay, is there anything that I can do here?
Yeah, I think you'll have to exit your share screen mode again.
Oh, share screen. Oh, that is this one, isn't it? Is it?
Okay.
Don't make it worse than it is.
Okay, let me. Oh, I have no.
This one.
I don't have the administrator. So.
Okay. Look, it doesn't matter. Let's get the. I don't mind.
Yeah, as long as we can start, maybe on the question and answer session, we can.
I have no problems. I have no. As I said, I can go on. That's not a problem.
Okay.
So can the presentation now?
Yes.
Yeah. So I'm ready whenever you are.
Yeah, wait a couple of minutes to see if more people get into the room. Maybe well, 3 o'clock, 5 minutes for you.
Tell me how to start and I'll start. That's it.
Okay.
See one a bar on the top of my screen. Arrow.
Oh yes.
Can you see the screen? There is a menu here.
Oh, menu.
You're wondering whether there is nothing that I have to click to share.
Maybe it's part of the WebEx option.
Yeah. Is not this one the one? This that's a or viewing or anything, isn't it?
If you can search, we can see the menu. We cannot see the menu.
I
But
see.
maybe there's an option to stop
Okay.
sharing the screen. Maybe you can open the camera for you to present.
Okay. Of your. No, that I can see here. Doesn't matter. So you can see the slides. That's more important.
De hecho, ya estaba grabando y yo creo que sí lo hice la vez pasada. Lo editó nada más.
Hello. Can you?
Yes, you, Dr. Niranjan.
You still can't see me?
Excuse-
Can you?
Yes.
Fantastic. Okay. That will the slide, isn't it? Now
Yeah, both.
you can see me as well as the
Yeah.
And I'm not blocking the slide.
No.
Oh, great.
You're out. Yeah. Good.
I can
I'll
hear you
vote.
loud and clear. Hello? Yes, I can hear you. Moses from University of Lincoln. I can hear you loud and clear.
Okay.
Yeah. Thank you, Professor.
So welcome everyone. Today we have ISFE webinar meeting. Today we have the pleasure to host Dr. Keshavan Niranjan from the University of Reading. He will be talking about boxing foods. And well, Niranjan, if you could please start your presentation, and thanks for accepting with your participation.
Thanks so much. It's a pleasure talk to so many people all around the world. I'm delighted to be here, and I'm grateful to the to the International Society of Food Engineering giving me this opportunity. For those of you who are still not very familiar with what the International Society of Food Engineering stands for, it is an independent society, but it is also the food engineering subject interest group of ISFE. And as I said, it's a great pleasure to give this webinar. Talk about bubbles in food as a subject area which has fascinated me for a number of years. And the main reason why it has fascinated me is because I trained as a chemical engineer, and I did my PhD on the behavior of bubbles in chemical reactors and then in bioreactors. And I started working in the food area. I continued my interest in bubbles and then realized that there are so many food items which contain bubbles. In fact, they owe their very quality, mouthfeel, etc. tons of bubbles. So it was in that context that I got that I entered this subject, and what we'll do today is to present perhaps an overview of the sorts of work we are trying to do. And in a nutshell, what we are trying to do is to understand the science or the processing science of formation of bubbles in foods, as well as how these bubbles enable us to perceive the quality of the food. One second. Yep. Now, clearly, bubbles are something that fascinate us. In children, I mean, you don't have to be a scientist to be fascinated by bubbles. Here's just a photograph of children playing with bubbles. It's a very common sight, and bubbles have always fascinated human beings. This is not just a kind of modern phenomena. There are also many period paintings where you can see bubbles forming the subject of the painting. You can see in this slide as well that there's a child who is absolutely fascinated with bubbles. Bubbles been included in food, especially foods such as bread, beer, champagne, celebratory drinks. So these products, it's the bubbles that really dominate in terms in defining the mouthfeel and quality perception as well. We're also finding that new bubble-containing products are appearing almost daily on supermarket shelves. Almost all, or a significant proportion of products tend to contain bubbles, and the reason for this is something I will mention in a short while. Now, in this area, I must admit there wasn't that much literature in this area. This was in the 1990s. So when my first PhD student, Adrian Massey, he started his PhD, he said, what kind of literature do I survey? And I said, before you survey your literature, it's useful to go to the supermarket and find out what are the products which contain bubbles. I told him that you can go to these supermarkets and buy all the products which contain bubbles. He came up with this photograph here, and you will see the first thing he bought was a bubbly wine. I think it's not very expensive champagne, but it is definitely a wine that is sparkling wine. And then, of course, these fizzy drinks. So let us try and look at this picture a bit more scientifically. So you see that you have liquid phases like or fruit juice or all these are essentially aqueous solutions, maybe flavored aqueous solutions. And what we are trying to do is to absorb carbon dioxide in these in the aqueous solution, and of course we get a supersaturation, and we open the bottle or whatever to drink it, the bubbles start coming out, and there are more bubbles that are released as we drink, and therefore the entire perception of these products depend on how many bubbles are released on the surface of the tongue and how they pop on the surface of the tongue, and that's what creates the fizz in a fizzy drink. Of course, there's one thing that creates fizz, and that is very important, in fact, because we use carbon dioxide. We know that carbon dioxide dissolves in aqueous solutions to form a relatively weak acid. Now, when acid falls on our skin, it generally bites us. In other words, we feel some sort of irritation. Now, what happens? The tongue is one of the most sensitive parts of human body. So when we drink an acidic solution, clearly there is a sting on the surface of the tongue, but that sting is what we perceive as fizz. So whatever we understand as fizz, it's essentially a combination of two things. One, the bubble popping on the surface of the tongue, and secondly, it's the acid irritation that is caused on the surface of the tongue. So it's a combination of these two that causes fizz. So what happens in fizz drinks? So look at this picture. You also have you can actually analyze the products in terms of the viscosity of the system that is being into which you are including bubbles. So at one end of the viscosity spectrum, you have the aqueous solutions like Coca-Cola or orange juice. On the other end of the viscosity spectrum, you have something like a bread dough. So even a bread dough initially, when you're mixing, it doesn't have that much of gas, but you add the yeast and you stand for a while, and you will see that the bubbles start building up, and it starts build of bubbles and expansion, which is absolutely critical in the case of bread. But bread is, again, the dough is a very viscous system. In fact, it's a viscoelastic system. On the one end of the viscosity spectrum, you have aqueous solutions. On the higher end of the viscosity spectrum, you have viscoelastic systems like dough. And in between, you have a range of materials, such as, for example, ice cream. Now, ice cream is clearly, it has a significant viscosity, but it's certainly not like dough, but it's definitely far more viscous than water. Same thing as far as the mousse is concerned, or even chocolates. So all these systems are what I call intermediate viscosity systems, and most of the food products are essentially bubble included products where the bubbles are included into what I call the intermediate viscosity systems. Please note that in the case of ice cream, the volume fraction of air could be as high as 50 to 60%. And ice cream is also sold by volume in most countries, perhaps all countries, not sold by weight. So the next time you buy half a liter, I've actually bought about 250 mils of air, and you have also paid for it. I feel cheated, but that's a fact of life. It may not cost much, but including air and keeping it stable within the ice cream costs quite a bit. So that's what you are paying for. You're not paying for the air on its own. So that happens in the case of ice cream. Then, of course, you have chocolates, and I'll talk a bit more about chocolates. But please note that the cream biscuit is also a bubble included product, and I'm not referring to the biscuit as such. It's true that the biscuit also has voids and and it is porous, but the cream, which is essentially, it is not a dairy cream, it is a fat sugar synthetic mixture, and it is that fat sugar mixture which is often not dead, but certainly you have nitrogen bubbles being included, because if you aerate or oxygen, then there is a chance that the fat can get canceled. Therefore, what manufacturers do is to include very small nitrogen bubbles in the fat sugar matrix. And these bubbles are pretty small, probably of the order of 10 to 15 microns. So obviously, we won't be able to see these bubbles unless you have an externally strong eyesight, which is very unlikely. But the presence of these bubbles, even if we can't see it, matter, but we can definitely feel it in the mouth. And therefore, if you have cream biscuit where there are no bubbles included, you will be able to tell the difference between a good cream biscuit and a not so good cream. So there are all some of the products into which but included. And this is a very old slide. There are a lot more products, a number of new products, and all the products contain new products. They contain bubbles. So the natural question that one would ask is, what are bubbles important in the food? First of all, you will see that it gives a very favorable ratio of the volume to the amount of material. So you have a significant volume of material, but the actual volume is much smaller. Just as in the case of ice cream, you may think that you have bought half a liter of ice cream, but remember 250 mils of the half a liter is air. So get a favorable ratio of volume to the amount of material. So even though you have a substantial proportion of air or any gas, incidentally, when I say aerated, it does not necessarily mean only air. The food industry uses a range of gases, and so gas itself is a food ingredient. But there is no legal requirement to declare any of these gases, and secondly, those gases are actually not present in the food by the time you consume the food. But they will serve as a structure developing aid and then vanish. And what is left is essentially air. So that is why whether you call it, I'm using the term aerated food in a very general sense. Please note that air does not necessarily mean including air. You can also put other gases. Because whether you use air or any other gas, all these are zero-calorie food ingredients. So that is the greatest attraction these days, with obesity and all kinds of problems being or health problems being attributed to food. One of the most harmless ingredients would be gas or water, because they don't add calories, they don't stick to our body. Now, so even though they don't stick to our body, generally perceived sophistication as far as the mouthfeel is concerned. So when you eat or drink a bubble-containing product, we somehow naturally associate some kind of sophistication. It is psychological, and the reason that I think is that some of the earliest bubble-containing products are celebratory drinks like champagne and others. So when you are celebrating, you obviously open a bubble-containing drink. So naturally, we tend to associate bubbles with something positive, something sophisticated, and something very celebratory. So there are always these good attributes that we associate with bubbles. Perspective. Remember, bubbles with the help of bubbles, the manufacturers can produce a number of novel products which can potentially give the manufacturer market advantage. Now, in theory, I believe that you can take any conventional recipe, and if you are able to absorb bubbles and hold in the system, you end a product that looks different, perceived to be very different. So I think you can always create a bubble containing, say for you have a normal chocolate, a bar of chocolate, but you put bubbles in that bar of chocolate, it becomes a different product. And it also becomes a product that is seen positively by the market. Bubbles, they confer novelty and, of course, luxury in calories. So that is a huge advantage. Now, science point of view, what may have got to understand? What method to use to produce the different. Here we are talking about a dissolution of gas bubbles in a continuous phase, and the continuous phase is not entirely viscous liquid, or it may be even an aqueous solution. So that means how do you put the bubbles in? The second part is, of course, how to then examine the quality of the dispersion that is formed. Now, here I have to mention that historically there is a lot of work that has been done on foams. And by foam, what is a foam? Foam is essentially bubbles trapped in a broad liquid phase. So there's nothing new as far as study of foams is concerned. But most of these studies are actually by physical chemists, and you will find that physical chemists, by and large, I'm not saying all, but most physical chemists, what they tend to do is to create a foam and looking at the stability, interface, and all kinds of properties. So they are actually studying a foam that is already formed. From the point of view, we will not be our approach because the foam containing or the itself is a product. And therefore, what we should do is not examine a foam on its own. The foam that you form depends on the way you have produced it. So from engineering point of view, our approach has to be very different, and the main difference is that we are not just looking at a foam like physical chemists do, but what we do is to look at the quality of the foam that is formed with the method that is used to produce it. That link is of critical importance to food engineering. For us, from a food engineering point of view, the foam is the product, and the product has to be manufactured. There is no point in just looking at a foam on its own and then trying to look at its characteristics. What we have to do is to examine how the foam was formed in the first place, and then try to link the form of the foam with its stability, because then we will have a method to produce the product as well as examine the key quality, shelf life of the product. That's what is, these are the two main aspects of science that we food engineers must concern ourselves with. That are normally used to incorporate bubbles into foods. The range of methods, and I have only listed a few here, few important ones, of course. Most common method is, of course, mechanical agitation. That means you take a mix. It's a bit like a domestic whisk. If you're making cake, you're baking cake at home, you have to start making the batter. And you have a whisk. It's like a cage whisk. I'll show you a photograph in a minute. But these cage whisks, you can sort of whip the batter, and then, of course, you can put in a mold or whatever and then bake it. Mechanical agitation is the most common method used to create addition of gas bubbles in a batter. Now, I generally don't put this in, but that's trapped. So the gas gets trapped because when we use the whisk, there is air in space. That means in the space above the batter. That air essentially gets into the batter as you whip, and of course, once it gets in, it starts breaking down into smaller and small bubbles, and you end up getting a whipped batter. Most common way of making foams, which is mechanical agitation. Please note there are other ways of making foams as well. Creating a porous structure, and one is, of course, say, puffing or frying, or the Starbucks method of making cappuccino. In all these, what we do is to make use of steam to create the food structure. The question is, how does steam create the food structure? Well, in case of puffing, let's say popcorn, you corn. The corn is only about 3 millimeters or 3 to 4 millimeters in terms of size. And what happens? You start heating it, but you heat it very rapidly. When you heat rapidly, the case of the corn tends to form what we call a case-hardened layer. Now, relatively non-porous layer, so the water that is inside the corn is trying to come out. But the porous layer stops the water from coming out, and therefore the water keeps getting heated inside the corn and it gets converted into steam, and pressure inside the corn builds up. In other words, the corn itself behaves like a pressure vessel. Then, of course, the pressure becomes so high that the structure yields, and as it yields, the whole structure expands, and creates and puffs. Now, the puffing of a corn is a very exaggerated puff. In fact, the volume expansion ratios for corn can be as high as 20 to 30. So, in other words, if you strip a corn that's 1 mil, the corn can be 20 times that, 20 to 30 times the volume. So that is a very exaggerated puff, and that is why corn is so popular. It's very difficult to puff our materials. I mean, we can try and puff potato, we can puff vegetables as well, but don't expand 20 to 30 times. The maximum they would expand would be approximately the volume of water that they lose during the process. So, so let's say you take a potato piece which is mil, say in volume, and say it lost 2 mil of water. If effectively its volume should be 3 mil. However, because of puffing, you can probably bring it back to mil, but you make it 10 mil or 20 mil, and that would be quite a challenge. If you can do it, that's great. I think normal vegetables puff corn. Corn is an exception. So that is a good example of steam-induced puffing. Clean frying is also a method of creating post-structure, because what happens during frying, well, it is important to note that frying is also drying. Dehydration operation, I mean, it's very unfortunate that food scientists don't see frying as drying. People think frying is a separate unit operation. We will understand frying much better if we look at it as drying, air drying, or drying. So what happens is you take a product and use it in fat, and the fat is very hot, and the water inside the product boils, and clearly the steam comes out, and therefore the product puffs. Again, in frying also there is expansion, but the expansion is not like popcorn or something, but clearly you can get a very porous structure, and that porous structure is induced by during the escape of steam. Then the famous Starbucks technology for cappuccino, were almost hot beverages which contain milk are to some extent foamed. Some may be to a higher extent, some may be to a lower extent, but they are all milk is always foamed in these hot beverages, even in hot chocolates and all. And that foaming is quite interesting, and in fact it enhances the quality. But Starbucks sort of creates the foam. So see, what you do is to sparge steam into milk. Not steam, clearly the steam condenses, and therefore, because the steam loses latent heat, what's to happen is that milk also becomes hot. Now, as the steam enters the milk, at the tip, it's like a Venturi effect. Engineers will understand Venturi very easily. So the steam comes through Venturi. At the tip of at the narrowest point of the Venturi, the energy is the highest, pressure is the lowest, based on the well-known Bernoulli's equation, and therefore, because of the low pressure, if you stick a pipe which allows air, then the air itself gets sucked in, and so you always have a mixture of air and steam that is going through the milk, and that's what causes the creation of a foam. So these are all different ways. So you can either have mechanical agitation or you can have steam. You can have chemical methods to create a foam. And chemical methods, what I mean is there are very broadly speaking, two types of chemical agents. One, of course, using a chemical raising agent. For example, sodium carbonate, sodium bicarbonate. The carbonate bicarbonate gives off carbon dioxide, which helps create a porous structure. And then, of course, fermentation is also another way. There are many products where you make batter first, but then ferment it. That fermentation can be catalyzed by adding yeast, or maybe the environmental bacteria itself can ferment if the temperature and things are right, and create a foam. There are many products where the batter is actually fermented, and not cakes, but certainly products like many products. I'll come to that in a crumpet is a good example where you start with a batter, you ferment it, so you have lots of bubbles because of fermentation. Then what you do is to wait for all the bubbles to escape and baking. And the reason why you wait for all the bubbles to escape is because we don't want big bubbles baking. We want the bubbles to be as small as possible. In other words, what we do is to have a nuclei. The growth of bubbles is very similar to the growth of crystals. You have nucleation process and the nucleus grows into a crystal. The same way you have a bubble nucleus, and that bubble nucleus grows into bigger bubbles. If you have big bubbles to start with, during baking you will see that the product will simply disintegrate. And therefore, in all these where you have a fermented batter, what they do is, okay, the fermentation creates a lot of bubbles, but then you wait for all those bubbles to escape. And once they escape, you have small nuclei that are left. And when you bake those nuclei grow and develop into a very nice dispersion, which we will all, which we like, especially in terms of mouthfeel. Some other novel methods of creating bubbles. Aerosol is a good. Aerosol. When there are a number of personal care products which form an aerosol. So that means you have a liquid and you also have a gas, both coming together at the same time to form a foam. So all the aftershaves and the bath products. So there is a range of personal care products, and the same technology can also be used to create something like whipped cream. So you have whipped cream, but you don't whip it. Instead, use the aerosol technology to create a foam. So all you need is so you want a quick whipped cream, just use aerosol. And then, of course, the Guinness came up with a very novel way of creating a foam, and this is to create a draft beer. A draft beer is essentially beer where which has a foamy head on the top. Now that foamy head only have been a few years ago could have been created in a pub or a bar. What happens is, in a bar you have a pipe which dispenses the alcohol, and you also have a pipe that emits carbon dioxide. So you can have the carbon dioxide and alcohol mixing and creating a foam and a foamy head. But if you want to have a draft beer sitting in your house watching the television, you can buy a can of beer, but how do you get the foam in a can? And I think solve that problem by using a capsule called widget, and that capsule has gas under pressure. When you open the can, the capsule also bursts, and that gas release forms a nuclei, and then of course that initiates the release of bubbles from the supersaturated alcoholic drink, and that builds on the top of the can as a foam. So clearly you can have a draft beer now sitting at home, which would not have been possible a few years ago before the widget technology. Not that, now Guinness has also licensed its technology. It's not just Guinness that uses draft beer this way. This has licensed this technology even to their competitors. So you can now probably get draft beers of all brands, which with the help of this technology. Now focus on mechanical agitation, because even today mechanical agitation is the most common industrial way of incorporating bubbles. So it's a batch process. The old process were all batch processes. So you would take the batter and other things, and then you would simply, spark the gas and whip it. Nowadays, almost all the processes have become continuous, and the type of mixer that is used is the most common one is what's called the Mondo mix. And in the Mondo mix, what you have is a mixing head in which you have stator and a rotor. Which look more like a gear mechanism, and the rotor rotates. The continuous phase and the gas both enter the mixing head. The gas then, the mixing head also operates under pressure. And so what happens? Now, here's the main scientific contribution of some of the work that came from our laboratory. Initially, people were thinking that the mixer breaks the gas into bubbles. You get smaller and smaller bubbles if you have faster and faster rotation of the impeller. That is actually not the case. What tends to happen in the case of food systems is that you have pressure building up in the mixing in the mixing head, and under pressure, the gas dissolves more or less. So virtually all the gas that is allowed into the mixer head dissolves in the system, and then you release the pressure, the dissolved gas desorbs, and that's what causes the foam. So in other words, there has been a very fundamental change in our understanding of the mechanism of formation of bubbles. Earlier, it was thought that hydrodynamics played an important role, but today we have established that it is mass transfer, that is absorption of gas and desorption of gas, which creates the foam. That is the reason why if you use different gases, you tend to get different types of foams. Hydrodynamics was controlling the process of formation of a foam, then I think we would have had the same result with all the gases. And very well that different gases give different types of dispersion, and therefore we attribute this to the solubility of the gas and the mass transfer processes. Now, this is what happens in a positive pressure process. Please that when continuous processes started earlier, there were many processes which were reliant upon drawing a vacuum. So we used to dissolve a gas and then vacuum, and that vacuum would release the gas and it would create foam. But food industry seems to have more or less moved out of this negative pressure, and today we only use positive pressure. Now here's an old whisk. It's a whisk. You can see the impeller, which is exactly like a domestic impeller. Domestic whisk. You have to put batter or whatever into this vessel. Make sure that you don't submerge the whisk completely, because if you do that, then you won't have air getting in space. So you partially submerge with batter, and then of course rotate it, and you can also run this under pressure. So that's a process. What are parameters that you measure? First of all, we need to know what are the common parameters which characterize a person. Very broadly speaking, the most important parameter is what we call hold up. Food scientists, I think engineers call this hold up, and food scientists call this overrun. Now, it all depends on whether it's the hold up or overrun. There's a conceptual difference. The formula may be different. Because in one case, you measure it on you measure the volume of gas on the basis of the volume of dispersion. In the case of overrun, you measure it as volume of gas per unit volume of the continuous space that you take. Therefore, what tends to happen is, we have a volume fraction here, and that volume fraction can be easily measured on the basis of density. So it's a very easy measure density, and the density can be related to the volume fraction. So it's not a difficult experiment to do. Here we have graphs which show how the volume fraction varies as a function of whipping time. Now, this is very important from the food engineering point of view, because engineers have to tell how long you should mix, because time variable. So we'll see that in most cases, the volume fraction of gas absorbed increases, it reaches a peak, and then it drops. Now, so you see, there's a sponge cake batter as well. It goes up, reaches a maximum value, and it drops. So naturally, the question now is, when stop mixing? Should you stop mixing here? Should you stop mixing here? Here? Where? And not with that. If you want, let's say 30% air, you can 30% for 4 minutes, or you can get 30% by mixing for 2 minutes. The question is, will you use 4 minutes or will you use 15 minutes? So these are the engineering decisions that we have to take. And remember, engineers are very mathematical in their training, and therefore we often get very excited when we see turning points like this. When something goes up and comes down, we generally become very excited, and we think that we should aerate the cake batter so that the maximum amount of air is included. Generally not the case, because if you have too much air included, then the product becomes very brittle, it's not robust, and it disintegrates. So it may expand during baking, but as soon as you stop baking, it collapses as well. Remember, the structure is very important. The structure must be strong, and once a product expands, it must remain in an expanded state without collapsing. So how much you aerate will not depend on maximum amount of air that you can put into the system. It depends on you have to do humor test. In fact, it is only a sensory analysis that will tell you how much air you can incorporate. So it's the general pattern. Because this is run under pressure, we can also try to sort of, what is the holdup. If you know the holdup at one pressure, you can always find out what is the holdup at another pressure. But here, of course, we are simply using the Boyle's law to do this calculation. Here, a flow diagram of a cream biscuit mixer, and you will see that this device, commutator, this is here you have a mixing head, and in the mixing head, you will see first you have a gas coming in. You also have a closing pump which lets the feed here. All are mixed, and then of course the pressure is released, and when the pressure is released, the bubbles are dissolved, and that's then dispensed on the biscuit surfaces, which probably be some here on a conveyor. That's how you match your cream biscuits. So it's the dissolution of the gas that is important. Absorption and desorption together create the dispersion characters. Experiment which was actually patented by Nestle here, and that is way back in 2006, where tried to dissolve gas, a fat, chocolate fat. Now, so under pressure, say about 2 or 3 atmospheres, you can dissolve the gas. Now, when we release the pressure, what we did was, we did not release the pressure to atmospheric pressure. Instead, we took from 2-3 atmospheres to a negative pressure. Now, when there was a substantial amount of gas that is released, and we get foams which had over 90% air. Now, if you get a foam that has more than 90% air, the problem is, what do you do with such a brittle foam? It's very weak foam. But what we found was, when you make it dissolve under positive pressure and release it all the way to a negative pressure, then what happens is you also get a structure that is quite strong. In fact, the chocolates that contain 90% of air could be molded into shape. And that's attraction, and that's what resulted in this process. The bubble size. Now, clearly, the hold up only tells you what is the volume of bubbles that is present. To measure the bubble size, the bubble sizes are very important, because you can have the same volume of gas, but you can have very different bubble sizes. So one method of measuring bubble size is what we call X-ray tomography. In X-ray tomography, what we do is it is based on X-ray attenuation. So you have a sample, let's say an aerated chocolate that's kept here. The chocolate has bubbles, so have X-rays. The attenuation of X-rays by the chocolate is much more than the attenuation by bubbles, because the density of the bubbles is almost 1,000 times less. So when you do that, you get a good contrast, and that contrast can be intensified, and you can always view image, and you can something like this. These are all chocolates which have been aerated with different gases. So it's the same chocolate is aerated. One is aerated with carbon dioxide, one is aerated with nitrous oxide, aerated with argon and nitrogen, and you will see the structure of product is completely different. With carbon dioxide and nitrous oxide, you tend to get more bubbles, you also tend to get bigger bubbles. Whereas with argon and nitrogen, you get fewer bubbles and you get smaller bubbles, and it is also evident in the holdup. Let's say, so in the case of carbon dioxide and nitrous oxide, you can get 68% holdup, whereas with the same gas under the same, in the same chocolate under the same mixing conditions, you get half the holdup when you use argon and nitrogen. And the reason is very simple. Carbon dioxide and nitrous oxide have a much higher solubility than argon and nitrogen. So the solubility, you get what we call macro-aerated product. The solubility, you get micro-aerated product. Macro-aerated products are easy to bite. Micro-aerated products are slightly harder to bite. And all depends on the consumer liking. At the end of the day, don't make a product because you like to make it. You only make a product because the consumers like to eat it. If the demand in the market for harder products, then go for microaeration. If there is a demand for brittle products, go for macroaeration or use more soluble gases. And you see that you have different bubble sizes. Incidentally, when you use techniques like tomography, it is important to note that you are only focusing the X-ray on a plane, on a cross section. So you're not getting 3 bubbles. Here you are getting 2D bubble sections. So what you are seeing here, they are essentially 2D bubble sections. They are not 3D. So if you want 3D images, what you have to do is to focus X-rays on different planes. And when you focus it on different planes, you can stack all the images together. And when you do that, you can get a virtual chocolate. So this is what I believe the world's first virtual chocolate. You can see bubbles, traditional bubbles recreated, and then of course you can measure the bubble size. Most bubble size distributions in food products are normal distributions, and you can always calculate a statistical mean and standard deviations. Now, also presented the chocolate to panel, and we got this response. To the left side, we have texture attributes. To the right side, we have mouthfeel and sort of flavor attributes. And you see that the argon and the nitrogen, they essentially is yellow and the green. So you see that the same chocolate divided itself into 2 groups. One group which was harder, and that was the micro-aerated chocolate, and that was micro-aerated because we had nitrogen and argon, which have low solubility, and the other group which was porous and dull, and that's because we used more soluble gas like carbon dioxide and nitrous oxide. So what this graph shows is that you can create 2 or 3 types of products from the same base liquid, simply different gases. So you see, in new product development, it gives you a lot of ideas and a lot of degrees of freedom. The method which can be used for bubble size distribution measurement is confocal laser scanning microscopy. And here what we do is we use a laser, we use laser activated dyes in you are measuring the dispersion characteristics, and then of course you allow lasers to act these dyes, and the images you get, you are able to sort of tell structure. So we have actually applied this to milk foams. You can see bubbles. You have different bubbles. This is a 2-dimensional image. Please note, not a 3-dimensional image. What this shows is that you will see that depending on where you focus, you will see different. You have to be very careful when you are using these techniques. These are very useful techniques, but they have also got to be properly used because there can be artifacts, as I am demonstrating here. Now you will see that these two bubbles, number 4 and 5, you can see the same bubbles here as well in two images. The vicinity of these bubbles are completely different. And the difference is one is actually taken on one plane and this has been taken on a slightly different plane. So when you take images at different planes, the same bubbles may appear different. And that is because the plane itself is actually breaking the bubbles at different locations. In some cases, it may be breaking it close to the equator. In some cases, it may be breaking it close to the pole. There are artifacts, and you have to be very careful when you are interpreting such images. You will see that in the vicinity or the region of the bubble can be completely different. Here, see, between bubbles 4 and 5, in between there are very few bubbles. But here, you look at between 4 and 5, there are so many other bubbles which are visible. So it all depends, and you've got to be very careful while interpreting these images. Now, again, that's a two-dimensional image, so you can stack these images and you can get a three-dimensional structure, which you can examine, and you can get three-dimensional images. In fact, you can also get a four-dimensional image as here, where you can assume time as a variable, and you can actually monitor the disintegration of the foam with time. So these are all possible now in terms of experimental techniques. So take individual bubbles and then monitor their the changes in their diameter as a function of time, and based on the changes in diameter, you can find out the mechanism that is called the breakup of the foam or disintegration of the foam, and that you can then counteract by changing the formation so that you can then sort of have a foam that lasts longer. I think we're almost near the end now. Not possible to do what happens at the interfaces. For example, if the laser dye can be specific. So you can have a dye that attaches to the protein. You have a dye that attaches to the fat. So you can see the interface, and you can also tell what component is present at the interface. Now, this is actually a milk foam at 37 degrees. 37 degrees is a relatively low temperature. You can have some fat which in the phase. Fat starts melting at about 20, 25, 26, and then by 40, most of the fat are in a state. But you have some fat in the solid state. It is possible to view it, and you can see that the can stabilize, in fact, the bubble here, as shown in the case. If you take the temperature very high, then you will find that the fat is more or less liquid. It has gone away from the interface, and you can see. So these bubbles are probably stabilized by the proteins or something else that stabilizes it, which I will talk in a minute. Now, another way of examining interface surrounding a bubble is to look at what I call bubble ghosts. Now, what happens is these are all, if you see this image here, these are X bubbles. They were bubbles, but the gas has gone. Once it's gone, you still find the interfacial components sort of accumulating. So examining these interfacial components, you can tell what was stabilizing the foam. So that is yet another technique to examine the foam interface of a foam. In the book, please note that chemical processes also influence the foam formation and stability. The heat treatment is a very basic parameter characterizing processed milk. You can have a low heat treated milk, or you can have a very high heat treated milk. In treated milk, you have more native proteins. Native proteins are relatively good as stabilizing the interface is concerned. But if you're having denatured proteins, then in other words, you increase the heat treatment, there is denaturation, so you do not have that many bands here. So what this electrophoresis bands, incidentally, and you'll find that these proteins are not very good at stabilizing foams, whereas these are. However, we found especially in the case of Starbucks type foam, is even though the protein was denatured, the foam tended to be a bit stable, and we attributed that to casein and a protein forming a network around the bubbles. So when proteins when the caseins and whey proteins form a network around bubbles, then bubbles can be stabilized, and that is how you can have very, very stable foams, even though the milk is extremely, very highly milk treated. We have a direct proof, the two of casein and whey proteins forming a network, but we found that if you remove the casein, so we actually found out, we removed casein from milk, and we found that the foam was not at all stable. So I'm suggesting that's a direct proof. Now, the method of creating foams is actually, so steam injection, mechanical agitation, and third method is air bubbling. That means pass air through a liquid, and in a liquid is placed in a glass, and you start bubbling air. That's what is called bubble columns in chemical engineering. And so these bubbles accumulate at the top. I mean, of course, a part of the bubbles escape, a part of the bubbles get trapped, and you have a foamy head. And these bubble foams are usually, used in, relatively low temperature drinks. If you have a milkshake or a cold milkshake, then you can hear bubbling. And especially in the context of a vending machine, you can. Now, the type of bubbles here also is quite interesting, but here doesn't go down in the case of milk. The bubbles, the hold-up increases, and then, of course, it becomes flat. So actually correlate the hold-up variation as a function of time by this equation, and you can find the constants alpha and beta as a function of temperature. You can find it as a function of milk quality. You can find it, as a function of sparger design, etc. Please note that these are not tall bubble columns. Most of the literature on bubble columns are for tall bubble columns. But food systems only aerate about 200 mil or 300 mil. And therefore, these are relatively short bubble columns, and therefore the sparger design becomes very important from an engineering point of view. And different spargers will give you different bubble sizes, different hold-ups, and therefore different mouthfeels. So here, the characteristics of milk foams, it actually depends on the bubbling time. Higher foam times, they tend to form big bubbles, and they also form less stable foams. So we don't want big bubbles in the foam. We want relatively small bubbles. At the same time, we also want uniform sized bubbles. If the variation in bubble size is very high, or the standard deviation is very high, then these bubbles start coalescing, and that also makes the foam unstable. So ideally, you want small bubbles, but uniform sized bubbles. So what are gaps in this area that we have to address? From a process engineering point of view, we still do not understand the link between the operational parameters and the product quality. I think understanding is restricted to some specific systems. It's not a generic understanding, and I think this is an area where we have to focus as engineers. In process engineering, we also have to understand product engineering. And what I mean by product engineering is how do we design and formulate products with targeted mouthfeels. So in other words, if the marketing person comes and tells you, I want a product which feels like this in the mouth, can design it. I think it is the job of an engineer to design, because design is something that, designing in my view, is an engineering skill. And design as process design, both hand in hand, because if we are not involved in product design, we will not be able to develop a good process. Right now, what seems to be happening is that chef and the food scientist is designing the product and coming in later and trying to develop a process. I don't think that is right. We must be involved and we equip ourselves with the skills to formulate product. And therefore, formulation engineering is something that we have to on as engineers. And this is an area where I think we are relatively weak, but we have to focus. I also have to understand the factors which influence dispersion stability. We are able to characterize the dispersion in terms of texture, rheology, bubble size, and other things. But what is the relationship between the instrumental measurement and mouthfeel? There is very little sensory done on containing products, and if at all these work has been done, they must be they have been done in companies, and information is really not available in the public domain. So I think the relationship between sensory response and instrumental response for bubble containing products is an area that really needs further attention. And lastly, understand what bubbles have on things like flavor release. Note that foams provide enormous gas liquid interfacial areas. So when you have high areas, the flavors would also tend to be released inside foams much more strongly. So a foam is inherently a strong a strong system for encapsulating flavors. And we don't understand much about relationship between foam characteristic and flavor perception. So these are some of the areas that require further attention, and I hope future research will focus on these things. So we will end my presentation, and I'm actually most grateful to all my colleagues, my PhD students, and people like Stephen Pountney, who helped us design the control laser system. I'm very, very grateful to Nestle because most of the work that I have presented today were funded by Nestle as well as the Engineering and Physical Sciences Research Council of UK. Thank you very much.
Dr. Niranjan, for the presentation. We have time for questions. Anyone in the audience who may want to Dr. Niranjan, please open up your microphone. Chat room, please.
Hello. It's Moses from National Center for Food Manufacturing, University of Lincoln. I would say thank you to Professor for this presentation. I just want to ask a question about measurement of overflow. Sorry.
Overrun.
Yes. Is that specific equipment to do that, or do we need to perform an experiment to measure that?
Okay. Right now, most of the overrun measurements are done offline. That means you take a sample and wait for the gas to disengage, because foam is an unstable system. Gas will disengage. Know the initial volume of the foam. You know the volume of the final volume of the liquid phase after dispersion has left. So you always calculate the overrun, but it's an offline method. Now there are online methods, but they are not direct methods, but direct methods. For example, when you have let's take something like a chocolate. The color of liquid chocolate, okay, which is dark brown. But when you start creating a foam, you will see that the color becomes lighter and lighter and lighter.
Okay.
It is possible to correlate the color of the foam with the volume of gas. So there are methods which we use and which we can, but these are indirect methods, and I think the advantage of indirect methods is that you have to be done offline. You can also do them. You can measure the overrun online.
Okay, thank you.
It is possible.
Thank you, sir. Another question is on the research gap. You mentioned that we see the link between the operational parameters and the product quality. What are these operational parameters are you referring to?
Sure. When saying operational parameters, well, let's say you are trying to create a foam by mechanical agitation, say by mixing.
Okay.
The question is, okay, what should be the speed of the mixer?
Okay.
Okay, what would be the pressure head? What should be the how much gas do you put in?
Yes.
And these are all because of the product quality depends on all these parameters.
Yes.
Right now, see, engineers are essentially here to design. Now, how design without knowing the link between your starting and the end product. What I was referring to, the link between product quality and process conditions.
Okay. Thank you very much, sir.
Yeah.
So, anything for Dr. Niranjan?
Can I ask this? Is Tim Moses? Hello.
Yeah, we can hear you.
Yes. Can I ask this from Professor? Can you host a visit of colleagues from other university at the University of Reading?
To show you around our laboratories and
Yes.
all.
Yeah.
Please. Yeah, just drop me an email.
I will contact you and let you know.
Please.
Yeah.
Yeah, you're welcome.
Good. Thank you.
The only thing is at the moment the device, the mixing device which was used different gases, that was actually in Nestle, so it was actually returned to Nestle.
That's not a problem. I'm just looking at
the
possibility.
To visit our labs, no problem.
Yeah, I'm just looking at the possibility of collaboration with the National Center for Food Manufacturing. Yeah,
no,
when I come.
You're most welcome.
Thank you, sir.
Yeah, I'm Nanisha. I'd like to ask some questions. You mentioned that bubbles can be stabilized by protein, especially native protein. And you said if it has more denatured protein, the foam is poor. Is correct. But the air is hydrophobic. Denatured protein is hydrophobic as well.
I'll explain to you what I meant. This is our studies relate to milk. Yes. And in general, if you native proteins, then they tend to, hydrophobicity may be one of the aspects, but they go and lodge themselves at the interface. If you denatured proteins, they are not interfacially active as native proteins. I was referring to.
Oh, okay. Yeah, thank you.
Yeah.
Dr. Niranjan? You mentioned the X-ray microtomography, laser confocal microscopy. There will be pretty much a focus on MR to attend this type of processes on the microstructure. Which other techniques do you think will help to understanding to fill these gaps, and within the next 5 years, which will be the most transcendent analytical techniques?
Yeah, this is a very difficult question to give a very general answer, but I will give you some pointers. I can't precisely answer this question because it's an open-ended question. If you look at the bubble sizes that we have investigated up till now, not in my laboratory, but in general, if you look at the literature, you will find that the bubble sizes probably vary. The smallest bubble size would probably be around 10 microns. And of course, at the larger end, you may have up to about 500 microns. That's the range measuring. Now, so the techniques that we have right now are essentially to look at microbubbles. Okay. Interestingly, what is happening now is that there are many processes where you are tending to use much small bubbles, and the papers have tended to call it nano bubbles. I don't know, but it's a nano scale bubble, but certainly they are much smaller than the bubbles we are seeing, that we are using now. I doubt whether the same techniques can be applied on a much scale. So we may need new techniques. Particle sizes can be measured. So it's not, so we may have to adapt techniques that are used in called nanotechnology. I must admit, I'm not entirely sure about what is nanotechnology, because it is, tens to hundreds of is also nanotechnology. But certainly, when the bubble sizes become smaller and smaller, we use the conventional techniques, micro techniques. We have to go for something close to the nanotechniques, and I think there will be some innovations in those areas, and that's what I foresee will happen in the next 5 years.
Okay. Any questions for the
I quickly ask, how do we contact Dr. Niranjan? Because I've checked the advertisement, I can't find the email there.
Oh,
yes.
The email. Look, the email I thought was given in my introduction. If not,
maybe I missed that.
Well, if you Google my name and University of Reading, you'll find my email address.
Yes, I know. Yeah, I got that. Thank you.
We also
there on the chat.
I posted it on the chat room. I don't know if you can see the Dr. Niranjan's email address.
Not fully on my screen. It's red.ac.uk. The K is missing there. Huh?
It's in here.
Yeah.
Yeah.
Or Moses Sahaji. I'm sorry, the pronunciation.
Ajay. Musajay.
Okay, I can send you the email address.
Yeah, I've seen it on the chat room. Yeah, good. Thank you.
Well, have any more questions, additional comments? I guess we will at this webinar session. Again, thank you, Dr. Niranjan, and everyone have a nice day.
Thank you very much. And if you have any questions, just email me. I'll be happy to answer.
That's wonderful. Thank you, sir.
Thank you.
Thank you.
Well, really well.
Oh, excellent.
Good audio and the presentation went smoothly, so
No, it's
really interesting to.
good. Is this recorded or how does it work?
Yeah, the webinar staff has been recording it. They will edit it.
And it will be on the web.
5 and we will send email within a place with a recording.
That's very good, man. Okay, I'm really pleased. Thanks for all your help, eh?
No, it's a pleasure.
Yeah, okay. Take care. Enjoy yourself. Bye-bye.